right, welcome everyone to the final section, the final part of Chapter 5. Here, we're going to continue our study, right, of the second derivative. And I'd like you to think this is breaking it down into two pieces, two separate pieces. The first is we're going to interpret concavity inflection points given instead the first derivative. We've played the game when you're given the original function. I'd like to play the game now if you're given the first derivative. And then, separate idea, we're going to see how the second derivative can be used to classify maxima and minima, an idea that we brought up back in 5.1. So, let's get to it with this first part. We're going to start with, we have a first derivative, back up. There we go. We're going to have a first derivative function, underlined. The graph is shown below, but I'd like to ignore that part for right now. I want to start, if you're given the equation, what do you do? So use the derivatives equation here to determine where f is concave up, concave down, locate any inflection points, you know the drill. So the idea is if you're given the first derivative equation, that, well, you can just take the second derivative and the game is pretty much the same. So let's do it. Okay, so I take the second derivative, aka the derivative of the derivative, and so I get 6x squared minus 6x minus 12. Of course, you want to know where is the second derivative, right? If you're trying to identify inflection points and stuff, you want to know where is this undefined or when is it 0? Well, it's never undefined, right? There's no division, so you can't divide by 0. There's no square root, so you can't take the square root of a negative. There's no natural logs, anything like that. So the only hope for inflection points is when this thing's equal to 0. So I'm going to set it equal to 0 and see what happens. And notice, well, I can divide everything by 12. So when I take 0, not 12, I want to divide everything by 6, sorry. When I divide 0 by 6, you still get 0. And then here you get x squared minus x minus 2. And this is just nice. It's really a cosmetic change more than anything else. And you can see that now this can be factored, right? So this is going to be probably x minus 2 and x plus 1. So therefore, we have potential inflection points when x is equal to 2 or when x is equal to negative 1. These are potential inflection points. I don't know yet if we actually changed concavity or not, but let's check. So I'm going to go ahead and draw my number line. I'm now interested in plotting information about the second derivative, and I need to break this up, right? A point of interest is at negative 1, and another point of interest is at 2. And I need to take some test points, so negative 2 maybe, 0 in this one, 3 in this one, and I need to plot this information, see if the second derivative is positive or negative there. So I'm going to go ahead and use my calculator for this part. So let's see here, y equals, and I'm going to plot, right, the second derivative. So there it is. So 6x squared minus 6x minus 12. All right, and we're going to go ahead and look at our table. And if we're doing things right, at negative 1, the second derivative is 0, and at 2, the second derivative is 0. So that's a good sign. So if I look at the point negative 2, we see that the second derivative there is positive, right? So I'm interested in the test point at negative 2. So there, the second derivative is positive. All right, how about at 0? At 0, the second derivative is negative. It's negative 12. And then at 3, the second derivative is again positive. It's positive 24. So now we have the answers to our questions here. We can see f is concave up on, well, less than negative 1, right, everywhere in this interval. So less than negative 1, so negative infinity all the way up to negative 1, not including it. Or if it's bigger than 2, so 2 to infinity. This is where it's concave up. This is where the second derivative is positive. F is concave down on the interval between that, right, between negative 1 and 2. And we have inflection points. F has inflection points at, and so it changes concavity from positive to negative at negative 1. So x equals negative 1 is 1. And then also at 2, right, because it changes from negative to positive. And all that we care about is that we actually have a change in concavity, right? So also at x equals 2. We should also point out that x equals negative 1 and x equals 2 are in the domain of the original function, right? It's a nice continuous function. everyone's happy. Okay, so there's our answer. Now the real challenge is that imagine if I didn't give you the equation and all I gave you was this graph here, right? And I still want to determine where does the original function f have, where is it concave up, where is it concave down, where does it have inflection points? What would you look for? Well, remember, if this is the first derivative right here, the second derivative is the derivative of the derivative, right? So we're going to ask a lot of the same questions that we did for the first derivative, but now we're going to do for the derivative of this thing. I know, a little bit confusing. So the first step, right, where is inflection points? That is, where is the second derivative equal to 0 or undefined? So the second derivative, that's going to be the derivative of this thing here. So we can see the derivative of f prime is 0 at -1 and 2. Those happen to be the same values up here, not a coincidence. So at x equals -1 and 2, we have potential inflection points. So the game is the same. You would draw a number line here. -1 and 2 are our points of interest. And now we need to figure out, because again, we're playing this as if we don't have the equation at all, we need to figure out, does it switch, where is it concave up, where is it concave down, etc. And does it switch concavity at these inflection points? So you would look maybe somewhere over here, like at -2, for instance, like we did before. So at -2, you would ask, is the derivative of the derivative, aka the second derivative, right, is this thing, aka, right, it's the slope, is the slope positive or negative? And you can see here that the slope of the first derivative, aka the second derivative, is positive. And likewise, you choose a test point maybe like 0, and you look at the slope of the derivative, aka the second derivative, right? And so you can see here that the slope is negative. And then finally, you choose another test point like 3, and you look at the slope of the derivative function, aka the second derivative, and you ask, is this positive or negative? Well, the slope is positive. And so you can see that we made the exact same number line in both situations. So we would get the exact same answer. You can just copy and paste this essentially. So we can actually determine when a function is concave up, concave down, and where are inflection points based on either an equation or a graph of the first derivative. Okay, so that's the first new thing that I wanted to go over with you guys. The second thing is that it turns out the second derivative can be used to classify minima and maxima, aka extrema. So the way that we do this is with this technique right here. So suppose that we've actually found some critical points. So x equals c in this case. It's a critical point. We're also going to suppose the second derivative at c exists, so it's not undefined, anything like that. So again, we're going to determine the critical points, figure out f double prime of x, so we're going to calculate this, not so bad, and then we're going to check the sign at the critical point. And the claim is, if the second derivative at this critical point is greater than 0, then our original function has a relative minimum. I know it's kind of weird because you would think greater than 0 may be maximum, but it's actually flip-flopped, right? So if greater than 0, minimum. If it's less than 0, then it has a relative maximum. Remember, sometimes we just say minimum or maximum. And then finally, if it's equal to 0, then the second derivative test here doesn't really help us out. So the claim is we need to use the first derivative test to determine whether or not f of x has a relative extrema at x equals c. This was, of course, the idea that we brought up in 5.1, where you take the first derivative and you look at the sign of the derivative to the left and to the right of our c. So this now brings up, right, a second derivative test. So I have two examples to emphasize this. The first example, I think, is maybe one of the purest forms of checking if you know the second derivative test. So here are a bunch of potential functions, a through c, and values. So which of the values below would, for the function f of x, would guarantee a maximum at x equals 2? So you can see we have f of 2's, we have f prime of 2's, we have f double prime, or the second derivative of f at 2. And right, we want to know which one would guarantee a maximum. And so the idea here is to use the second derivative test. So the first step for the second derivative test is, right, determine any critical points. So critical points is where the first derivative is equal to 0. So first derivative is equal to 0. That only happens, oops, erase. That only happens in cases B, C, and D. So this doesn't really help us, A or E. So in B, C, or D, the first derivative is 0. These are critical points. We continue. The next part, so we could calculate out the derivative, but we don't have a second derivative equation or anything like this here. We don't have an equation of the function even. So the next step, check the sign of the second derivative at C. So you can see if we're checking the second derivative, we have one case where it's positive, one case where it's 0, one case where it's negative. And we want to know, okay, which one would actually correspond to a maximum? And so the answer is D, right? So we want this to be less than 0. So -1 is less than 0. And according to this one right here, if the second derivative is less than 0, just like -1 is, then we actually have a maximum. Now, if you were to change this up and you wanted a minimum, right, that would happen at B. And then finally, C here, we don't have any information, right, because this is where it's equal to 0. So the answer is D. Okay, so like I mentioned, this is kind of maybe one of the purest forms of checking the second derivative test. I like this sort of question. And then finally, one with an actual equation. So consider the function f of x equals x to the fourth minus 4x cubed. We're going to find all the critical points, and then using B, we're going to classify critical points as minima or maxima using the second derivative test. So this is specifying that you have to use the second derivative test, even though, I mean, you technically, if it didn't specify, you could use the first derivative test. This is trying to test, do you, the student, know the second derivative test? So let's do it. Find all the critical points. So critical points are where the derivative is equal to 0. So find the derivative, 4x cubed minus 12x squared. We want to know when is this equal to 0. And so typically you want to factor these things, right? So the least common multiple, greatest common factor, the GCF, right? The greatest common factor between these, 4x squared. So there's a 4 and an x squared in both of these. So let's see, if I took out a 4x squared from the first one, there would be an x remaining. If I took out a 4 and an x squared, there would be a -3 remaining. So this is telling me, now that I have this factored, that the critical points are when x is equal to 0, that would make this first bit equal to 0, or when x is equal to 3, that would make the second bit equal to 0. And of course, 0 times anything would be 0. So here are our critical points, 0 and 3. And I'd like to classify these critical points as minima or maxima using the second derivative test. So we've already done, right, step 1. We figured out the critical points of f. Now I need to calculate out the second derivative. So step 2, f double prime of x is equal to, now I'm looking up here, right, I'm going to take the derivative of the derivative. So let's see, this is going to be 12x squared minus 24x, right? So there's the second derivative. And I'm going to figure out these values. So 0 and 3, so I want to know what is the second derivative's value at 0 and what is the second derivative's value at 3. So if I plugged in 0 here, well, I'd have 0 squared times 12, that'd be 0, minus 24 times 0, so lots of zeros around. So this one's equal to 0. And then f double prime of 3, so that's going to be 12 times 9 minus 24 times 3. Right, so let's get out our calculator just so that we don't make any mistakes. And let's see here, 12 times 9 minus 24 times 3. Enter. That's positive 36. So positive 36. So now we go back and we remember the second derivative test. And according to the second derivative test, this one cannot be classified. Classified. Yeah, that still looks horrible. Classified using the second derivative test. Deriv test. Because the second derivative there is 0, right? And so that was the conclusion. However, this one, we see the second derivative at this critical point is positive. And because the second derivative is positive, we know that this is going to be a minimum. So this is x equals 3 is minimum. Of f of x. Okay, so there we are. That's how we can use the second derivative test to classify minima or maxima. All right, that is the end of chapter 5. I'll see you guys in class.